Welcome to your AP Statistics discussion of Chapter 4. Last time we talked about categorical data and how to display it. Today we're going to talk about the same thing, but with quantitative data. So, especially when you have a whole bunch of numbers, it's really hard to summarize what you're looking at when all you have is the large set of data. So, one of the best ways to get a feel for what's going on as a distribution and the data as a whole is by looking at a visual display of the data. And one such way is to make a histogram. Now, if you are going to be making a histogram by hand, here's the steps for it. I would suggest entering the data into your calculator and letting it work its magic. But just in case you ever need to do this, you need to make bins, and those are going to be equal width piles of observed values. So here we're talking about earthquake magnitudes. And so what this means is since the first bin, it appears to be 0.2 in its width on the Richter scale, then the next one has to be 0.2, the next one 0.2, next one 0.2, so that we are talking about equal widths of our possible value. And then you're going to count how many observations fall in each bin, and you're going to make sure that the height of the bars of your histogram reach the height of the appropriate number of observations. One thing that's really different about bar charts and histograms, bar charts you intentionally put space between each of the bars. The only time you have space between bars of a histogram is if there's a bin with no observations in it. This is what's called a continuous numerical scale, and so endpoints should touch each other. A relative frequency histogram just displays the percentages of cases in each bin instead of the count. Again, if you're comparing one population to the other, frequently using relative frequency or percentages is the better way to make those comparisons because you're not likely to have the actual same number of observations. Okay, stem and leaf displays are wonderful, especially for small sets of data, because not only do they show the distribution of the quantitative variable, it preserves the individual values. So let's look, we've got a histogram and a stem and leaf display for pulse rates of 24 women at a health clinic. Which graphical display do you prefer? Well, that's a rhetorical question for you. Let's look at both of them. So here we can see in the histogram clearly there's a mode here in the early 80s. We can see it varies from around 55 up to around 90. There are a bunch of pulse rates where there seems to be an even distribution. So you get some good information from that. You get the same information from a stem and leaf display or stem and leaf plot. But the nice thing about it is that you actually can see what the individual values are. If you're going to calculate specific values to represent the center or the spread of the data, that's really nice to have all those values in a nice ordered list. Okay, so when you construct one, you're going to cut each data value into leading stems and trailing digits. And then you're going to use the stems to label the bins. Now, here are our stems. This is actually what's called a split stem. And what that means is that each stem is written twice, and observations between 0 and 4 go in the lower or the first stem, and then observations from 5 to 9 go in the second stem. That's when we do this when that really helps us see the distribution of the data better. Most of the time, though, you're going to have an ordered list from 0 to 9 of all the leaves that we have. Okay, in this case, all of the ones digits. In a minute, we're going to construct one ourselves, and I'm going to talk about the merits of, instead of going from greatest to least, going from least to greatest. But either way is acceptable. So one thing you want to note is that the leaves can only have one digit. So that means you're either going to have to round or truncate values sometimes so that you summarize every number with 2 digits, okay? The stem digit and the leaf digit. Because an observation like 84 could mean 84, okay? If we have 8 bar 4, that could mean 84, but it could also mean 840. It can mean 0.84. We always have to give a key as with an example of just one value and what it actually means in this context. So 8 and then a little line 4 means 84 beats per minute because we're talking about pulse rates. And as always, you want to label your stem and leaf display with a meaningful title. We always want to do that in AP Statistics. A dot plot is another simple display that is very helpful and gives you a lot of the same information as a histogram. So what you do is you place a dot along an axis. It can either be along a vertical axis. Honestly, normally we see them along a horizontal axis. Your calculator, this is going to be the first way it summarizes data when you go to graph it, and then you'll tell it if you want a histogram or something else from there. But there's nothing wrong with having one where the variable of interest is on the vertical and the frequency is on the horizontal. That, since it can be oriented either way, that's why it's so critical to label the axes as well as giving a meaningful title. So the dot plot at the right shows Kentucky Derby winning times, plotting each race as its own dot. You might see a dot plot displayed horizontally or vertically. So again, just repeating what I just said. Now, these are particularly helpful when you have many repeats of the same value. That makes it a really nice method for seeing how your data vary. Okay, so we want to provide more information. Okay, you've got this picture, you have an idea of the general trend, but it's also going to make it a more complete picture if you can describe 3 things: shape, center, and spread. And then in a minute, we're going to talk about, okay, what about values that just don't fit into the overall pattern? And those are going to be outliers. Okay, so when you're looking at the shape of a distribution, whether it's a histogram, stem and leaf display, or dot plot, you want to look to see if there's a single central peak or several separated peaks in the data. In other words, values where the most observed observations lie. One thing you want to know is the histogram symmetric, or does it have some other shape which we'll call skewed? And do any unusual features stick out? So peaks. Does the histogram, and we're just going to use histogram, it is true for stem and leaf displays and dot plots also, have a single central peak or several separated peaks? So what does this mean? Peaks in a histogram are called modes. And if there's just one big peak, it's called unimodal. If there's 2 clear separate peaks, it's called bimodal. That's really interesting because sometimes you have two groups that have been lumped together as one. And with the single peaks, if you can look at some variable that indicates that the reason for there being 2 peaks, you can see that maybe you really have 2 populations of interest. And if there's 3 or more peaks, we have what's called a multimodal distribution. So here's a picture of a bimodal histogram with 2 apparent peaks. You can see that there's clearly one at a lower value and one at a higher value. And so one of the things you'd want to do from there is look for the variable that explains why this exists. A histogram that doesn't appear to have any mode and in which all the bars are approximately the same height is called uniform. Okay, so now let's talk about symmetry. The question is the histogram symmetric? It's essentially the same idea of symmetry that you've had throughout mathematics. And basically, it's going to be if you can draw a vertical line through the middle and flip the edges over, they would match pretty much pretty closely. In other words, the left half of the data and the right half of the data are roughly mirror images of each other. Remember, we're dealing with real data, and so perfect symmetry is gonna be almost impossible to have. Okay, we're looking for rough symmetry. Okay, another way to describe the shape of a distribution is if it's skewed. And a skewed distribution is going to have a tail where the values, you know, the values that are observed go further in one direction than the other. And there will be few observations in the tail, but the direction of the tail tells you the direction of the skew. So the tail tells, not the mode. So if you look here, we have a left skewed distribution. And what that means is that the observations that are made extend further to the left than to the right. You can see it trails off further here to the left than to the right. So again, it's the tail that tells you the direction, not the mode. Okay. Right skewed distribution, that means you're going to have values on the upper end, on the right end, that trail off. Okay. You have just a couple of cases of them, but it's going to go much further away from the mode than the left tail. And so the right tail that trails tells us the direction of the skew. So this is right skewed. All right. The other thing you want to look at is there anything unusual? And there's basically two things you're looking for: outliers and gaps. And an outlier is a large or small value that stands off way away from the body of the distribution by itself. A gap is where there is a gap, but the data aren't really far from each other. It's almost like you have one set of data and then another. So again, with the gaps, just like with the bimodal distribution, that's another indication that there may actually be two subgroups that should be considered instead of one large group. All right. The following histogram has outliers. Okay, there are 3 cities in the leftmost bar that are clearly far away from the rest of the distribution. So they lie outside of what we expect, so they're called outliers. One of the things that's incredibly important is being able to tell the center of the distribution. It's easy to find the center when a histogram is unimodal and symmetric. It's right there in the middle. On the other hand, it can be a little more challenging to find the center of a skewed histogram or a histogram with more than one mode. So the median is the value that will divide the data exactly in half. So you'll have as many observations below the median as you do above it. So just like the median in the middle of the road divides the road into two equal sides, the median of the distribution does the same thing. So if we're looking at a histogram, another way to think of it is that it's going to divide the histogram where you have the same area to the left and the same area to the right. Spread is also important to talk about. Okay, 2 distributions can have the same center, but have very different looks to them. So if you look, it's critical to know that we have values that are tightly clustered around the middle or that are more spread out. If they're tightly clustered around the middle, when we talk about standard deviation in a minute, that means we have a small standard deviation. And when they're more spread out, we're going to have a large standard deviation. So this distribution to the left has less spread than the distribution to the right. So anytime you are describing a distribution numerically, you want to give the center and the spread. You don't want to just tell the center because that doesn't give the whole picture. Imagine these are test grades, and there's one test where here's the center and there's very little spread. Okay, and over here we have another test, same center but a much larger spread. Um, those are telling two very different stories. On the left, you have a test where the students performed within within a reasonable range. Over here, man, you'd want to look at why there's so much variability among the student scores. The most basic way to describe the spread is by giving the range. And the range is the single number that is the maximum minus the minimum. Okay, don't list the minimum and maximum for the range. Do the subtraction, because in statistics it means this very specific definition and that one value. A disadvantage of the range is that a single extreme value can make it very large and thus not representative of the data overall. Let's go back to the test example because we all are familiar with that. Let's say a test is given where most students score between 85 and 100, but then there's one student who scores a 42. The range would be very misleading in that case. Another way of measuring spread, in fact, if you have a skewed set of data, the preferred way to measure the spread is by calculating the interquartile range, called the IQR. And this lets us ignore extreme data values and concentrate on the middle of the data. So you're probably going, okay, great, interquartile range. We're going to be looking at the difference between a couple of quartiles. So what are the quartiles? One big warning I have for you: do not try to make an analogy between statistical quartiles and Houston Christian quartiles. They're completely different. So if your brain starts going there, just tell it to stop. They're not really analogous. Statistical quartiles divide the data into 4 equal sections. Okay, I almost think of like a stick of butter divided in 4 equal, with 4 equal marks on it. And 1/4 of the data lies below the lower quartile. 1/4 of the data lies above the upper quartile. The middle quartile, Q2, is just the median. So the quartiles border the Q1 and Q3 border the middle half of the data. So here's the cool thing. Like I said, a stick of butter, you think of the quartiles on that and they would be equally spaced. That's because the stick of butter is equally distributed. If you were looking at it and one end was very thin, to have the same amount of butter, the distance between the beginning and then where that quarter ends is going to be much wider than one that has a larger amount of butter, a higher stack of butter, if you will. So it's going to be interesting to work with the quartiles, I think. The difference between the quartiles is called the interquartile range. And so it's the upper quartile minus the lower quartile. So Q3 minus Q1. The lower and upper quartiles are the 25th and 75th percentile of the data. So the IQR contains the middle 50% of the values of the distribution as shown in the figure. Okay, so the area in the pink are all the observations between Q1 and Q3, and so the distance from Q1 to Q3 is the interquartile range. Just as a reminder, remember the percentile. If I say the 25th percentile, that is the observation where 25% of all observations fall below it. 75th percentile is the percentile where 75% of all observations fall below it. Now, one way to summarize data that's very helpful is the 5-number summary. And the way that we do that is we are going to give the two extremes, minimum and maximum, and the quartiles and the median. Okay, so for our earthquake example, The magnitudes in the the 5-number summary looks like this. So the minimum is 3.7. The value of the first quartile is 6.6. The value of the second quartile, or the median, is 7. And the value of the third quartile is 7.6. And the value of the maximum is 9. And so what's cool about this is 25% of the data fall between the minimum and the first quartile. 25% fall between the first quartile and the median. 25% fall between the median and the third quarter, and 25% of the observations fall between the third quartile and the maximum. So another way to summarize what's going on in a distribution is by using mean and standard deviation. Now, this really is best used whenever you have a symmetric set of data. Okay, so the mean is just what you think of as the average. When you normally think of average, you're thinking about a mean. You add up all the values and divide by the number of values. So the mean feels like the center because it's the point where the histogram actually balances, which for when it's symmetric totally makes sense and looks normal. For skewed data, that's a little more difficult. So why do we only use the mean whenever we have symmetric data, and then use the median, in any circumstance, certainly if we have skewed data? The median considers only the order of the values. It is resistant to values that are extraordinarily large or small. Think about if you have a bunch of quiz grades, or in our class, problem set grades, and you've made high A's on most of them, but you throw 1 0 in there, that is going to lower your average, your mean, tremendously. But if we use the median, where we count it into the middle observation, having a lowest grade of 0 or having a lowest grade of 70, given that all your other grades are above 70, would make no difference in what the median is, but the mean would be pulled much lower. Okay, so we call the median resistant to outliers, and the mean is not resistant to outliers. The mean does, however, have some cool characteristics about it, and mean and standard deviation are nice to use. So if the histogram is symmetric and there are no outliers, use the mean. The really cool thing is if a distribution is perfectly symmetric, the mean and the median will be equal. If the histogram is skewed or has outliers, you are better off using the median, and for spread, the IQR. Mean and standard deviation are buddies and always go together. Median and IQR are buddies and always go together. So what about the spread with the symmetric distribution? The standard deviation is great to use if you know the mean. It's based on the mean. You actually use the mean to calculate it. So it's only paired with the mean. And the nice thing about it is that it does take into consideration how far each observation is from the mean. So a deviation is the distance that a data value is from the mean. Okay, it's going to be x minus x bar. That's the deviation. Because of the way means are calculated, if we took all the deviations and added them up, they would always add up to 0. So that's not meaningful. The way we work around it is we take the square of them all, so the x minus x bar squared, then we add up, and then we're going to divide not by n, but n minus 1, and then we'll take the square root. So what does that look like as a formula? So here we have sigma notation, which means add the following. We're going to take each value of x, and we're going to subtract the mean, okay, the x bar, and we're going to square it. And then we're going to take the next value of x and subtract the mean and square that. We're going to add all those up and divide by n minus 1. So why n minus 1? There's a theoretical explanation, and then there's a practical explanation. In statistics, practical explanations trump everything. You just get a better measurement. Okay, you get a better measurement if you divide by n minus 1, and then than you do if you divide by n. The theoretical explanation in its simplest terms are n minus 1 is what is called degrees of freedom. Since x minus x bar itself, okay, not squaring it, but the x minus x bar itself always adds up to 0, that means that when you get to the n minus first observation of the x minus x bar, you've reached the end of your freedom, because the last value for x minus x bar is already determined. It has to be whatever makes up the difference between the sum so far and 0. So there are n minus 1 degrees of freedom. Okay, so whichever way helps you to understand it and think about it, we divide by n minus 1. This gives us s squared, where s is our standard deviation. This value is called the variance. And the variance is great. In fact, we need variance later whenever we do some cool things of adding random variables together. But the problem of it is it's in squared units. So that distorts it and makes it hard to pair it with the mean. So what we have to do then is take the square root of that whole thing. So our standard deviation is the square root of the sum of the deviations squared divided by n minus 1. Yes, figuring this out in a data set of any reasonable size is a pain. That's why we love our calculators, and we're going to let it do the just the tedious calculations for us. All right. So when data values are tightly clustered around the center of the distribution, the IQR and standard deviation are going to be very small. When the data values are scattered far from the center, the IQR and standard deviation will be large. Okay, so again, whenever you are describing a distribution, make sure to mind your socks. You want to give the shape, outliers, center, and spread. So Socks the Sock Puppet, I actually have a Socks the Sock Puppet at school. If I forget to bring out Socks the Sock Puppet, ask me about socks and I will show you socks. It's silly, but it helps you remember, okay? You want Socks the Sock Puppet to come out and help you make that description of the distribution. All right, so since most of what we have involves a lot of visuals, I'm going to let you look at the text to get the reference of the problem that we're using for our example. So look on page 73 at problem 12. Go ahead, pause the video, go get your textbook, look at it. Okay, so for part A, I would expect the mean to be larger than the median due to the effect of the large outlier. Okay, so if there's an outlier, it's going to pull the mean toward it. So if there's a large outlier, the mean's going to be larger than the median. If there's a small outlier, the mean will be smaller than the median. Okay, so the distribution of emails is skewed to the right with a mode near 1. Okay, so that's shape and center. One outlier is very far from the rest of the data. So that's outliers. And the spread is small with most of the data less than 6. So there's spread. So we've got our description there. We've got shapes. We've got outliers. We've got center. And we've got spread. Again, for problem 8, we're going to look at the textbook. It's on page 72. We want to describe the distribution, and then can you account for the features you see here? All right, so for this distribution, it appears to be bimodal with one peak near 65 inches and one near 71 inches. So there we've got shape, roughly, one part of shape describing the fact that it's bimodal. Primarily, this first sentence is about center. It's kind of hard to say that there's one meaningful center because you have the two modes. One's at 65 and one is 71. There could be two groups that look fairly symmetric within each group. Okay, so more into the symmetric there. And then the overall spread is 16 inches. If you want to mention there appear to be no outliers, that would actually even improve this. Can you account for the features you see? Well, it's a quire. Men tend to have an average height that's larger than the average height of women. So, one plausible explanation is that there's probably men and women in the choir. All right, again, just turn the page over to page 76. Look at problem 37. We're going to create a dot plot for these data, and then we're going to describe the distribution. Describing distributions is going to be something that you need to be able to do like I want to say in your sleep, but I really hope you're not dreaming about distributions. But it's something you just that needs to be second nature. We're going to then generalize it to be able to compare distributions, and you'll need to make sure you hit each of those features: shape, outliers, center, and spread. Also, if you're doing a comparison. All right. So what we're going to do is we are going to open a page in our calculator. Okay. And then you're going to insert a list and spreadsheet page. Okay. In list A, you have to give it a name in order for us to do anything interesting with it. So we're going to call it hurricanes. All right. I saved my page here, my document, as Hurricanes 2006, so that I could just cut and paste it in here and it would have a meaningful title and it would have a nice label here of what's going on the horizontal axis. For the dot plots, sometimes it's not going to give you the label of count on the vertical axis, but it's going to give you a nice picture. Whenever you transcribe this to your paper, you will want to put count on the side. So here we've got the number of hurricanes. I enter the data set into my list. Now, in this case, I just went ahead and said to graph it. What I think is better, it's kind of a pain to have to go back and forth with the split screen. What I would prefer that you do, and I think you'll prefer that you do, is if you will add a second page to your document and you want to add the data and statistics page, not the graph page, data and statistics. And then you'll pick hurricanes as the variable that you want on the horizontal axis. Otherwise, it's just going to be this random set of dots that looks like a cloud of dots. And it will give you this nice picture, and you'll be able to go back and forth between the pages a little easier than it is with a split screen. All right, we want to describe the distribution. The distribution is slightly skewed to the right with no outliers. The mode of the distribution is around 2, and the overall spread of the data is 7. In class, I'm going to show you how to do something called one variable statistics, or if you want to play with it, you can. Just come over here and tell the calculator on your spreadsheet page that you want one variable statistics. You're only going to look at one list. The list you want, you can either reference it as A or as hurricanes. Okay. And what it will do is it's going to give you the mean, the standard deviation, all kinds of measures down toward the bottom. It'll give you all the values for the 5-number summary. It's really useful. If I don't automatically do it in class next time, remind me and I will show you how to do one variable statistics. Okay. 17 women were asked how many pairs of shoes they own. We want to create a stem and leaf display of their responses. When you're doing a stem and leaf display, unless you want some of those summary statistics from the one variable statistics I mentioned, don't bother putting all of this data into your calculator because your calculator won't create a stem and leaf display. Luckily, it's pretty easy to do by hand. Okay, so I prefer to do my stem and leaf displays from smallest to largest. That way, if I turn the display to where the stems are on the bottom, I can tell the shape of the distribution easier, because if it's skewed to the left, the skew is going to be to the left. If the skew is to the right, the skew is going to be to the right. If you reverse the order, if you go from least to greatest, your skews are going to be backwards. So I would suggest getting in the habit of going from least to greatest. So notice that since you have some values with just one digit. Okay, we're going to put 0 for the tens digit for those observations. And then we just go through and we look for all the single digit observations, and we go from least to greatest. So 4, 6, 7, 8. And then we do all of our observations that have a 1 in the tens place, 2 in the tens place, and 3 in the tens place. Now, if these two observations have been 43 and 45, and so the 30s wouldn't have any observations, you would still write the 3 and then write the 4 because you would want to show the gap. Now find the median, IQR, the mean, and standard deviation. Again, I would enter this data at this point into the spreadsheet on your calculator, label it with shoes because you have to do that, and then do one variable statistics on the list of shoes. Now, again, remind me tomorrow or whenever we meet in class to show you how to do this on the calculator, or if you just look up how to use one variable statistics on the CAS. If you Google that, I'm sure videos will come up and we'll show you. All right. Stem and leaf displays make it very easy to count to the middle data value, which is 20. And then it's easy then to count to the middle data value of the lower half and get that Q1 is 9. And then to find the median of the upper set of data, which is 24.5, and subtract to get your median. The mean, you would add all these up and divide by 17, and you're going to get 18.1. Now, for standard deviation, you can do this by hand, but you're going to have to take each observation, subtract 18.1, square that, and then add it to the next observation minus 18.1 and square that, and then add it to the next observation minus 18.1 and square that. Divide that whole sum by 16 because we use n minus 1, and then take the square root. Or you can learn how to use one variable statistics on your calculator, and in your calculator, it will be designated as SX. I hope I've made it clear. I think it's worth the investment to learn how to use the CAS to do this, and to always make sure you've got a charged calculator in your backpack when you come to class. All right, guys, that's it. I hope you have a wonderful day. Try the problems to try on your own. We will go over those in class, and I will also go over how to use the CAS to do all these cool things, and make sure everybody feels good about this material before y'all start on your classwork. I hope you have a great day. If you have any burning questions, remember you can always email me.